this video, we're going to look at our final conic section, the parabola. So more than likely, the parabola is the conic section you're most familiar with and have probably already graphed. Typically, when you learn to graph a parabola, you learn about standard form ax squared plus bx plus c, and you learn about vertex form. We're going to focus on something that's a little bit closer to vertex form, and we're also going to look at some different components of the parabolic graph that you probably didn't graph before. So more than likely, when you learn to graph a parabola, you learn to identify the vertex, and then you probably identified the x and y intercepts. So while that is still an appropriate way to graph a parabola, we know particularly for x-intercepts that sometimes x-intercepts can be difficult to find. Sometimes they require the use of the quadratic formula, which potentially can be problematic because potentially it's going to give us values that are not easy to graph. So we're going to focus on finding some different points on the graph of the parabola that are typically a little bit more straightforward to graph. So even though our approach to graphing may initially look a little bit more complicated, typically it's going to generate points that are going to be easier to graph. So first off, let's give the official definition of a parabola just like we did for an ellipse and for a hyperbola. So our parabola is also defined in terms of distance. So a parabola is the set of all points in the plane that are equidistant from a fixed line. This is new. Typically we just talk about a fixed point or points. Equidistant from a fixed line, what we call the directrix of the parabola, and a fixed point, the focus. Now with a parabola, we only have one focus. So for an ellipse or a hyperbola, we have two foci. With an ellipse, they're oriented inside of the graph, in between the vertices, and then with a hyperbola, the foci are further out than the vertex. So if we're talking about a parabola, we have one focus. It's inside the parabola as the parabola opens upward. And in terms of defining the graph, the points on the graph in terms of distance, all the points on the graph are going to be equidistant from the focus, which is inside of the curve, and the directrix, which is going to be an imaginary line that's outside of the curve. Now the directrix is not an asymptote, but it does behave in a similar way in the sense that it gives us information about our graph, but it's not truly there. So keep in mind the focus will always be inside of our graph, a certain distance from the vertex, and then the directrix is always going to be outside of the graph, but as it turns out, it's going to be the same distance away from the vertex. Now we also have some other features of the graph that are going to give us a little bit more information about it and help us draw it a little bit more accurately. So the line perpendicular to the directrix that also passes through the focus. So if you imagine drawing a line that goes to the focus, the vertex, and then is perpendicular to the directrix, we call this the axis of symmetry. And more than likely you've heard that term before when you graphed parabolas previously. So the graph of the parabola is, not surprisingly, symmetric across the axis of symmetry. So think of that as the mirror edge. To the left of that particular line and to the right of that particular line, we have mirror images for those two sides of our graph. Now the point where that line, the axis of symmetry, and the parabola intersect is the parabola's vertex. And again, that's probably a point you're familiar with graphing. Now the distance between this point, the vertex, and the focus, which is going to be inside of the graph, is what we call the focal length of the parabola. So the distance between the vertex, which is on the graph, and the focus, which is inside of the graph, is the focal length. And as it turns out, the distance to the directrix is always going to be the same, which is, again, based on the definition for our parabola. So we're looking at points that are equidistant from the focus and the directrix. So as we go further along the graph in either direction, we get further away from the focus, but we're also the same distance away from the directrix, and that's how we form this particular graph, how we find its points. Now we need to graph more than just a focus and then a line of symmetry. because we can have any, or not a focus, excuse me, a vertex. We can have anything centered at that particular vertex that's symmetric across that line. We have infinitely many parabolas that look like that. But using the focus is what's going to help us get the actual shape of our graph. So what we're interested in, not necessarily x-intercepts and y-intercepts, what we're interested in terms of graphing a little bit more accurately is the width of the parabola. In other words, how wide it is as we pass through the focus. We call this the focal diameter of the graph. So it's the line segment that passes through the focus from one side of the parabola to the other. It's the width of that line segment. And finding the width of that line segment is going to tell us how we go from the focus to a point on either side of our axis of symmetry, which will then give us 3 points in order to graph. So this line segment that passes through the focus, it's going to be perpendicular to our axis of symmetry. It's going to be parallel to our directrix, and again, it's going to give us the width of our parabola. This is referred to as the latus rectum. So knowing what that line segment looks like, more importantly knowing how long it is going to give us the information we need to finish out our graph once we know where the vertex is, once we know where the axis of symmetry is. So essentially, if we take that line segment, the latus rectum, take its length, divide it in half, that's going to tell us how far we travel from the focus in either direction in order to get to the actual graph and get a couple more points that we can actually graph. Now, as with a hyperbola, we see parabolas in real life fairly often, whether we realize it or not. So for instance, the St. Louis Arch, if you've ever been to St. Louis and seen that, or if you've just seen pictures of it, is parabolic. It's opening downward. And then a satellite dish is also parabolic. So the curve inside a satellite dish, if we were to take a cross section of that, is also going to be shaped like a parabola. So let's talk about the equations and how we graph from different forms. So as with ellipses, as with hyperbolas, we're going to focus on graphing from two different points of view, either centered at the origin, so specifically we have a vertex at the origin, or centered at a new location with a vertex at a new location. Now, a commonly used standard form for a parabolic equation is one you've probably seen before. Y is equal to ax squared plus bx plus c. This is an expanded form of a parabolic equation. Now, while we can think of this as a standard form and it still is a correct form for representing a parabola, it's not going to give us the information we really want in order to graph from our point of view. So we're going to use a different form that's going to allow us to more easily identify the additional key features we need in order to get the graph of the function. So in this case, if we just want x and y intercepts, this particular form is going to be fine. If we want to focus on these other types of features of the graph, the focus, the directrix, this idea of this little line segment, the latus rectum, how we go from the focus to either side of the graph, having this particular form is not going to be very helpful. So the form we're going to use is going to look a lot more like the ones we saw for the ellipse and for the hyperbola. So we don't necessarily have an A, a B, and a C in this case. For a parabola, the value we're going to focus on is what we call P. So P is going to give us information about how far we have to travel to get from the vertex to the focus of our graph. So that particular distance is going to be the most important distance we have. Using that distance and adjusting it is going to give us all the information we need in order to be able to graph. So the focal length of our parabola, which again is the distance to go from the vertex to the focus inside of the graph, is going to be the absolute value of this number P. So P can be positive, P can be negative. Whether it's positive or negative gives us information about the graph shape, but the focal length, the distance from the vertex to the focus, is going to be the absolute value of that number. And then the focal diameter, in other words, the length of the latus rectum, that line segment that crosses through the focus and goes from one side of the graph to the other, is going to be 4 times the absolute value of P. And if we divide that particular value in half, that's going to tell us how to start at the focus and go from one side to the other side of our parabola. Now, we have a variety of different graphs we can see based on the values for P. So the value for P is going to tell us what type of graph we're looking at. So we can have a vertical parabola that's either going to open upward or downward. We can also have a horizontal parabola, which you may not have graphed before, that can either open to the right or to the left. Now, a vertical parabola, we're going to have a vertical parabola when the x is squared. So notice in the standard form you're familiar with, you're only going to have one variable that's quadratic. So in this case, the x is quadratic and the y is not. With an ellipse or a hyperbola, both x and y are quadratic. With a parabola, only one will be. So a vertical parabola, what we're used to graphing, x is going to be quadratic. So our equation is going to have a quadratic x and then a linear y, but it's not going to look the same as this. Here's the equation. It's going to be x squared, but we're actually going to isolate the x squared, and x squared is going to be equal to what we refer to as 4 times p times y, where p is this value we use to find the focal length. So keep in mind, if the number in front of y is negative, that means p has a negative value. If the number in front of y is positive, p has a positive value. Now, a horizontal parabola is going to result if we switch these values. So if y is quadratic rather than x being quadratic. So if y is quadratic, and we then have 4 times p times x, P is going to behave in the same way, but it means we have a graph that's going to open to the left or to the right. We think about it in terms of the axis of symmetry. So if we're talking about a parabola that has a vertex at the origin, the axis of symmetry is that dividing line that divides the graph in half. We've got symmetry to one side, symmetry to the other side. For a vertical parabola, our axis of symmetry is vertical. Specifically, it's going to be along the y-axis since we're centered at the origin. For a horizontal parabola, our axis of symmetry is going to be horizontal, specifically along the x-axis, because again, we have a vertex at the origin. Now, the orientation of the graph is determined by this value for p. So if p is greater than 0, in other words, we have a coefficient that's going to be positive, a coefficient that's going to be positive. That means we're going to open in the positive direction, whatever that means for something vertical, whatever that means for something horizontal. So if we're talking about a vertical parabola and p is greater than 0, that means our graph is going to open upward. It's going to open in the positive direction vertically. Now if we have a horizontal parabola and our coefficient is positive, which means p is positive, we open to the right, which means in the positive direction horizontally. Now, if p is less than 0, we know that means a vertical reflection. The first time you graph a parabola, having a negative involved is going to associate with a vertical reflection. So we go from opening upward to opening downward if we're talking about something that's vertical. We go from opening to the right to opening to the left if we're talking about something that's horizontal. So we actually have 4 different varieties of a graph, whereas with a hyperbola, with an ellipse, we only really see 2 varieties of a graph. So graphing a parabola, determining what we're looking at, is a little bit more complicated just because we have to make a couple different decisions rather than just the decision of horizontal versus vertical. So once we know what we're looking at, how it's going to be oriented, which of the 4 directions it's going to open in, then we can focus on finding those key features of our graph. So the first thing we want is going to be the focus. Now for a parabola, graphing the focus is actually going to be important because there will be some other points we graph that are distributed away from the focus, not away from the vertex like we normally see, or away from the center like we normally see. So the focus for a vertical parabola is going to be inside of the parabola. Now if we're talking about something vertical, it's going to be above or it's going to be below. So notice in this case we're keeping the x value constant, but we're adjusting the y value by p units. So if p is a positive number, that means it's going to be above the vertex. If p is a negative number, that means it's going to be below the vertex. So we don't actually have to differentiate between which is which, whether p is positive or p is negative. The way we find the focus is going to be the same, and the signs are going to take care of themselves. The direction is going to take care of itself just based on the value we have for p. So for a vertical parabola, we hold the x constant, and then we adjust the y value using this value for p. So our focus, our single focus, is going to be at 0, p. And again, if p is a positive number, that's going to be above the vertex. If p is a negative number, that's going to be below the vertex. Now for our horizontal parabola, our focus is also going to be inside the graph, but that means either to the right or to the left of our vertex. So that means we're holding our y coordinate constant, and we're just adjusting the x coordinate, either so that the focus is to the right or to the left. So holding the y constant and just adjusting the x coordinate. So the focus is going to be p, 0. And again, if p is positive, automatically that's going to take us inside a graph that's oriented to the right. If p is negative, that's going to take us to the left of a graph that's oriented to the left. Now, once we know p, we can also determine the equation of the directrix. So the directrix for a vertical parabola, if the axis of symmetry is vertical, the directrix is going to be horizontal. Well, every horizontal line is of the form y is equal to a number. Well, the definition for the directrix is that it's the line that's equidistant from the vertex but outside of the parabola. And in this case, it's going to be a horizontal line. So if we go p units, be that positive or negative, to get to the focus, we go negative p units to get to the directrix. Now, keep in mind that doesn't always mean that the directrix is going to be y is equal to a negative number. If p is positive, then this evaluates to a negative number. But if p itself is negative, then a negative times a negative will evaluate to a positive number. So the signs are going to take care of themselves. All you really have to remember is take p and flip its sign. That's really all you have to remember. Now, if we're talking about a horizontal parabola, our axis of symmetry is horizontal, which means the directrix is perpendicular to that, and it's going to be vertical. So any vertical line is going to be of the form x is equal to a number. And again, it's going to be x is equal to negative p. So notice if we're adjusting the y coordinate for the focus, the directrix is of the form y is equal to. If we're adjusting the x coordinate to get the focus, then the directrix is of the form x is equal to. And then last but not least, the axis of symmetry. It's going to be oriented in the same way as the graph. So for a vertical parabola, it's going to be a vertical line of the form x is equal to. And it's always going to be x is equal to the x coordinate of the vertex. So 0 in this case. And then for a horizontal parabola, the axis of symmetry is going to be horizontal, again passing through the vertex. So a horizontal line is of the form y is equal to, and it's going to be y is equal to the y coordinate of the vertex, which in this case is 0. Okay, so that's a lot, and honestly we change things in a slightly different way than we do for an ellipse for a hyperbola. So I would say from the standpoint of graphing a conic section using these kinds of equations, graphing a parabola tends to be the most complicated graph just because we are truly dependent on where the focus is. Whereas with the other graphs, we just need vertices and then we can typically go from there. We actually do need to graph the focus in this case, and then we use the focus with this idea of the focal diameter in order to find additional points on our graph beyond the vertex. Okay, so let's look at a couple of examples. So we want to identify each parabola's vertex, its focus, its focal diameter, and then the end points of the latus rectum, that line segment that's going to take us across from one side of the graph to the other. And then we also want to write the equation for the directrix and for the axis of symmetry, those other lines that give us information about our graph. And then from that, we're going to graph the parabola. Now, graphing does not necessarily mean having to graph the directrix and the axis of symmetry, but it's not a bad idea to do so at least one time just to see how they relate to one another and how they relate to the actual graph. So let's start with just looking at the equation, seeing what we can see. So we know x squared, we have x squared, which means we have a vertical parabola. We have the one we're used to seeing. So if y is the linear term, we have a vertical parabola. So that means either it opens upward or it opens downward. So we make that additional determination by looking at the coefficient on y, or just the coefficient in general, the constant involved in the equation. In this case, it's negative, which means we open in the negative direction vertically. So opening vertically in the negative direction means our graph is oriented downward. So again, let's break that down. The fact that it's x squared means it's going to be vertical. And the fact that we have a negative constant tells us that we open in the negative direction vertically. So opening vertically in the negative direction means opening downward. Okay, so that tells us the vertex is going to be the highest point on the graph. It tells us our axis of symmetry is going to be vertical, and then everything is associated from there. So let's start by finding our value for p. We don't have an a, a b, and a c here. We have a p. So this coefficient on y, this is 4p. So if 4p is equal to negative 12, then p is equal to negative 12 divided by 4, which is going to be negative 3. So that tells us that from the vertex, our focus is negative 3 units inside of our graph. So negative here tells us we're going down in order to get from the vertex to the focus. So what is our vertex? Well, we're still looking at graphs centered at the origin, so our vertex is going to be 0, 0. So let's put that on the graph. Here's our vertex. Think of that as the starting point for the graph. From there, we are opening downward. The question is just how wide is our graph? And normally we could use intercepts. We might just find some random points in order to graph. Here we're going to use this idea of the focal diameter in order to determine where our focus is, where the additional points on our graph are. So what about our focus? Where's our focus going to be? Well, again, we're opening downward, which means our focus is in the same vertical line as this particular point, as the vertex, and it's going to be below it. So we're going to hold the x-coordinate constant and then adjust the y-coordinate by p units. In this case, p is negative 3. So hold the x-coordinate constant and then adjust the y-coordinate by the value p, which is going to give us 0, negative 3. So it's 3 units below the vertex, and it's going to be inside of the parabola. So here's our negative 3. Now, as with any other conic section, this point is not actually on the graph of the parabola, but whereas that point wasn't necessarily needed in order to graph an ellipse or a hyperbola, it is needed in order to accurately graph a parabola. So we do need to graph that focus in order to do the rest of the problem, essentially. So our focal diameter is defined as 4 times the absolute value of p, which is going to be 4 times the absolute value of negative 3. Well, the absolute value of negative 3 is going to be 3, so that's going to be 4 times 3, which is 12. Now, what does that mean? That means to go from one side of the parabola to the other, passing through the focus, we have to travel a total of 12 units. So what that means from a more practical standpoint is that there are half of that, 6 units, to the endpoints of the latus rectum, that line segment that passes through the focus and ends on the graph. So from that, we can determine where those endpoints are. And it's going to be helpful to look at the graph. We can graph these endpoints and then we can determine them that way. So the general idea is we're not starting at the vertex anymore. We're starting at the focus. We're transitioning from the focus. So from the focus, we have a vertical parabola. That means we travel horizontally to get to the endpoints of that line segment, the latus rectum. We travel 6 units in either direction, so 6 units to the right, 6 units to the left. So 6 units to the right would take us 1, 2, 3, 4, 5, 6 to one endpoint, an actual point on our graph, and then 1, 2, 3, 4, 5, 6 units to the left to take us to the other endpoint, and again another point on our graph. So notice the total distance from one endpoint to the other, that's a total of 12 units, which is referred to as our focal diameter. So how would we find those coordinates algebraically? Well, again, the idea is we're not starting at the vertex now, we're starting at the focus. So from the focus, we're going to the left and to the right a certain number of units, which means we're holding our y coordinate constant. So from 0, -3, we're going 6 units to the right, which should take us to 6, -3. And then we're going 6 units to the left, which would take us to -6, -3. And sure enough, those were the points that we graphed. So once we have those points, technically we have enough to get the graph. But let's finish out with the other key features, our directrix and our axis of symmetry. So if our focus is p units inside of our graph, then our directrix is p units outside of our graph. So in this case, p is -3. That means we're going to go up to +3 for our directrix, which is going to be at y is equal to 3. So because it's a horizontal line, it's going to be y is equal to 3. More specifically, it's y is equal to -p, which is going to be -3 in this case, which makes it positive. Now, I want to emphasize now, y equals is important. 3 by itself is just a number. Y equals 3 is a horizontal line, and when we're talking about the directrix and the axis of symmetry, we're talking about lines. Lines are represented by equations, so y equals, in addition to the 3, is going to be important. So if we were to graph the directrix, and at least for this example, I'll go ahead and put it on there, we're going to graph a horizontal line that is above the vertex, p units above, if we think of the absolute value of p. Okay, so the focus is -3 units from the vertex, the directrix is +3 units from the vertex. And then our axis of symmetry, in this case we have a vertical parabola, so it's going to be the vertical line passing through our vertex. So a vertical line is always of the form x is equal to, and it's always going to be x is equal to the x coordinate of our vertex. So in this case, x is equal to 0. So if we want to graph the axis of symmetry, it's going to be the vertical line that passes through our vertex and through the focus. And because it's going to be right there on the y-axis, it's typically easier to graph if you go just to the left of that or just to the right of that, just so you can see the actual line. And as with asymptotes, these lines aren't really there, they're not really part of the graph, they're just giving the graph its shape. But once we have our vertex and we have the endpoints of the latus rectum, that's going to give us 3 points, it's going to tell us how wide the graph is and where the graph originates. So from that particular point, we can draw our curve. And so that's going to be our parabola. So notice, slightly different perspective than how you normally graph. But the benefit of graphing from this point of view is the fact that we don't have to focus on x and y intercepts. In this case, this graph only has one x-intercept, and it happens to coincide with the y-intercept as well. So if we just wanted to graph from the standpoint of using intercepts, we would still need additional points after we find those intercepts because we only have one intercept. That intercept happens to be a coinciding x and y intercept. So using the focal diameter, finding the endpoints of this lattice rectum, this line segment, gives us those additional points to graph regardless of what our parabola actually looks like, where its vertex is. Okay, let's try another example. So we have 2y squared is equal to 32x. Now I want to put this in standard form, and let's revisit that. So with standard form in either case, the big thing is that we want our quadratic term to be isolated. So in this case, our quadratic term is not isolated. So I need to start by isolating it. So I'm going to divide out the 2 in front of our y squared, which is going to give us y squared is equal to 32 divided by 2, which is 16x. So based on the structure of this, what do I know? Well, normally I have a quadratic x. Here I have a quadratic y. So the fact that y is quadratic tells me that this graph is horizontal. It's a horizontal parabola, which means either it's going to open to the right or it's going to open to the left. Now I make that determination based on the fact that our coefficient is positive. So because we have a positive coefficient, that means our graph is going to open in the positive direction. So opening horizontally in the positive direction means we're opening to the right. So this graph is oriented so that it opens to the right of its vertex. Now in this case, we're still looking at a vertex of 0, 0. So that's going to be the starting point for our graph, 0, 0. So from the origin, our graph is going to open to the right. Now from that, we can determine what the axis of symmetry is going to be. Let's go ahead and do that part because we don't need it to graph, but we want to find it. The axis of symmetry is always going to be the line that goes through the vertex and around which we have a mirror image for our graph. So because we're opening to the right, the mirror image is going to be above and below the x-axis. So we have a horizontal axis of symmetry, so it's of the form y equals, and it's y equals whatever the y-coordinate of the vertex is. So it's going to be y is equal to 0 in this case. Okay, now let's focus on getting those additional points we need. So what we need now is P. We don't have A, B, and C, we have P. So P is going to be 1/4 of our coefficient. So if 4P is equal to 16, then that means P is equal to 4. And pretty much anything else we need to know, we can determine just from that value of P. So let's think about our focus now. We're opening to the right, which means our focus is going to be to the right of the vertex. It's going to be P units to the right, which means we're holding our y-coordinate constant for the vertex, and then we're just adjusting the x-coordinate to get to the focus. So hold the y-coordinate constant, and then adjust the x-coordinate. So we have a focus at 4, 0. Now again, that point is not on the graph, but it's going to be used to find some points that are on the graph. So next, what is our focal diameter? It's going to be 4 times the absolute value of P. Think of it as just taking the absolute value of whatever the coefficient is in this case. So the absolute value of 16 is going to be 16. So that means it's going to be half of that. It's going to be 8 units to the end points of the lattice rectum to get to the actual graph through the focus. So let's see if we can make this determination algebraically before we look at the graph. So we're starting from the focus. If our graph is opening to the right, that means the focus is inside of that graph. It means the endpoints of the lattice rectum are above and below the focus. So we're holding the x value constant, increasing the y, decreasing the y by this many units. So the end points of the lattice rectum are going to be at 4, 8, and 4, -8. So those are going to be the two additional points we need in order to be able to graph. So 4, 1, 2, 3, 4, 5, 6, 7, 8. And then 4, 1, 2, 3, 4, 5, 6, 7, 8. 8 units in the negative direction. And once we have those, technically we have enough to graph. So passing through the vertex and each of these endpoints, something like that. And so let's finish by finding the equation of our directrix. So the directrix is going to be the line that's outside of our parabola, that's the same distance away as the focus. So the focus was 4 units in the positive direction. The directrix is going to be 4 units in the negative direction, so negative p. Now because we have a horizontal parabola, it means the directrix is going to be vertical. So it's going to be of the form x is equal to negative p, which in this case is going to be -4. So if we wanted to graph the axis of symmetry, we have our directrix, we have our axis of symmetry. So that, roughly speaking, is what's going to happen when we have a horizontal parabola, which may be new to you. Okay, so now let's talk about what happens when the vertex shifts. And based on what we know about ellipses, about hyperbolas, you can probably guess essentially what's going to happen, how the new equation is going to be structured. So P is structured the same way, P is used the same way, we find it the same way we did before. What changes is what's happening to x, what's happening to y. So for our vertical parabola, we know that's going to occur when we have x squared, not y squared, so y is going to be linear, x is going to be quadratic. If we have shifted our vertex to the location h, k, that's indicated in our equation by subtracting these values from their respective variables. So x minus h squared is equal to 4p times y minus k. So essentially where we had an x and y, we now have x minus h and y minus k, which represent the shift of the graph, and they also represent the new location of the vertex. So vertex is h, k, like we're used to seeing. Now for a horizontal parabola, we have a quadratic y and a linear x. So that's going to be y minus k squared is equal to 4p times x minus h. And then we're going to find our p the same way. P plays the same role, but keep in mind, now when we find the focus, the directrix, the endpoints of our lattice rectum, we're transitioning from a new focus, which resulted from a new vertex. So we're going to have to be very careful when we find these coordinates, given that we're no longer centered at the origin. So let's think about our focus. So we're starting at a vertex of h, k. Okay, so our focus is going to be inside our graph. Vertically means it's either going to be above or it's going to be below p units. The sign of p is going to take care of that for us. So if it's above or below, we're holding the x coordinate constant and we're just adjusting the y coordinate by p units. So hold the x coordinate constant and then adjust the y coordinate by p units. So k plus p. And again, keep in mind, if p is negative, it really means we're making the y coordinate smaller. It doesn't necessarily mean that it has to be getting larger from adding on p. If p is positive, it's getting larger. If p is negative, it's getting smaller, which means our focus is going down from the vertex. Now, if we're looking at a horizontal parabola, our focus is either to the right or to the left of our vertex, which means we're holding the y coordinate constant and we're adjusting the x coordinate by p units. So h plus p, comma, k. So what about our directrix? Well, if we're talking about a vertical parabola, the directrix is horizontal. It's p units in the opposite direction away from our vertex. So let's break this down. So number one, it's going to be horizontal. So it's going to be of the form y is equal to. Now y is equal to what? Well, we're starting at our vertex, h comma k, and we're going negative p units away in terms of the y value. So y is equal to means we're associating with the y value of the vertex. So we're starting at k and we're transitioning negative p units away. Now again, keep in mind, this doesn't necessarily mean the number is getting smaller than k. If p is positive, then in fact we are subtracting a positive number, it's getting smaller. But if p were negative, subtracting a negative means we're actually getting larger. So the sign of p is going to take care of that for us. Now if we have a horizontal parabola, we have a vertical directrix, so of the form x is equal to. It's going to start at the vertex and it's going to be negative p units away from the vertex. So x is equals, meaning we're starting at h and we're subtracting p from that x coordinate. And then our axis of symmetry for something vertical is going to be a vertical line. So x is equal to, and it's always going to be equal to whatever the associated coordinate for the vertex is. So in this case, x is equal to h. And then for a horizontal parabola, opening either right or left, we have a horizontal axis of symmetry. So y is equal to, and in this case, y is equal to the y coordinate of the vertex. So y is equal to k. And making the determination about how the graph opens, that doesn't change based on changing this form, adjusting where the vertex is. If we're looking at a constant that's greater than 0, we know we're opening in the positive direction, either up or to the right. If we're looking at a coefficient, a constant that's negative, that means we're either opening down or opening to the left. So this is probably going to be the most challenging thing to graph out of all of the conic sections we graph. Graphing a parabola once the vertex is shifted. So I can't emphasize enough, study these images, think about how the different components of the graph are related to one another. Or, more importantly, how the components of the graph are related to the vertex. Everything starts from the vertex. So once we know where the vertex is and we know how the graph is oriented, all of the other key features of the graph are determined in that manner. Once we know where that vertex is, everything else just flows off of making that determination. So let's look at a couple of examples. Okay, so same directions. We want to identify the same key features, the vertex, the focus, the focal diameter, and then those endpoints of the lattice rectum so that we can get an accurate graph. And then we'll find our directrix, our axis of symmetry, and we will graph. Okay, so number one, we are no longer centered at the origin. As soon as we have numbers added and subtracted from x and y, we've shifted our vertex. Now, how is this graph going to be oriented? Well, what's quadratic? In this case, y is quadratic. So because y is quadratic, that's our indication that we have a horizontal graph. And then opening right versus opening left is determined by the coefficient. In this case, the coefficient is -4. So because it's a negative coefficient, that means we're opening in the negative direction. So horizontally in the negative direction means we're opening to the left. So once we find the vertex, the focus is going to be to the left of that, the directrix is going to be to the right of that. Well, what is our vertex? Let's make that determination. So how has x been adjusted? How has y been adjusted? So x minus 2 means we have an x coordinate of 2. and y plus 3 means we have a y coordinate of -3. So our vertex is at 2, -1, -2, -3. Okay, and we're opening to the left, which means the graph emanates from that point and everything is going to the left. So the focus is going to be inside, it's going to be to the left of that particular value there at the vertex. Now we know the focus is based on our value for P, so let's determine what that is. So we know that 4P is equal to -4, which means that P is equal to -4 divided by 4, which is going to be -1. And remember, the signs are going to take care of themselves. So just using the sign we already have for P, that's going to take care of itself in terms of adjusting the location for the focus and for the directrix. So starting from the vertex, let's think about how the focus is going to look. So the focus is going to be to the left of the vertex, which means we're holding the y coordinate constant and we're adjusting the x coordinate by P units. So for our focus, we're holding the y coordinate constant and then adjusting the x coordinate by P units. So 2 minus 1, holding the y coordinate constant. So that's going to be 1, -3. Okay, so let's put that on the graph. So our focus is at 1, -1, -2, -3. Okay, now what about our focal diameter? It's always going to be 4 times the absolute value of P. Well, in this case, P is -1. We take its absolute value, and that's going to give us +1. So 4 times +1 is equal to 4, which means there are 4 divided by 2, 2 units to the end points of the lattice rectum. So what is that going to look like in this case though? So remember, when we're finding those endpoints, we're no longer starting at the vertex, we're starting at the focus. We're transitioning from the focus. So the graph opens to the left, which means from the focus, the endpoints of the lattice rectum are going to be above and below that focus. So certain number of units above, certain number of units below. What does that mean for the coordinates though? It means we're starting at the focus, we're holding the x coordinate constant, and then we're adjusting the y coordinate by that value we just found. So starting at the focus, we're holding the x coordinate constant, and then we're adjusting the y coordinate this many units in either direction. So 2 units above, 2 units below. So -3 above, below by 2 units. So what are those coordinates going to be? Well, we have -3 plus 2, so that's going to be -1. And then -3 minus 2 is going to be -5. So 1, -1, and then 1, -5. 1, -1, and then 1, -1, 2, 3, 4, 5. And once we graph what we find algebraically, we can verify that those endpoints make sense. They should be equidistant away from the focus. We know the focal diameter is 4, so if we look at the distance between those 2 points, it should be a total of 4 units. So the graph can verify the algebra and then vice versa. So once we have those 2 values, technically, we have enough to graph. So starting at our vertex, passing through each of those points, that's our parabola. So let's find our directrix, our axis of symmetry. Now we can graph those, and graphing them may help us with the algebra a little bit. So let's do that. So our axis of symmetry is the mirror image line that passes through the vertex and through the focus. So in this case, it's going to be a horizontal line. Now remember, it's not really there, so if we want to graph it, we graph it as a dotted line. Okay. And then the directrix is going to be the line outside of the parabola, so over here, that's the same distance away as the focus, just on the opposite side. So in this case, the focus is 1 unit away from the vertex, which means the directrix is also 1 unit away from the vertex, just on the other side of the vertex. So that's our directrix. Now we want to find these values algebraically, but we can use the graph just to make sure that our values that we find make sense. So the directrix, number 1, we're looking at a horizontal parabola, which means the directrix is going to be vertical. It's going to be of the form x is equal to. That means, since we're going in relation to the vertex now, we're starting with the original x coordinate of the vertex, which is 2. And then it's p units, or in this case, negative p units away from that original x coordinate for the vertex. So p is negative 1, so we're subtracting negative 1. It's always negative p units. So if p is negative, that means the focus is going to be to the left, the directrix is going to be the right in the positive direction. So 2 minus negative 1 is going to be 3. And notice that is in fact where the directrix ends up, at x equals 3. So the algebra verifies what we see on the graph. Now the axis of symmetry, we don't actually have to do any adjustments there. Since we're talking about a horizontal parabola, it's going to be a horizontal line, so of the form y equals, and it's always going to be the horizontal line that passes through the vertex that has a y coordinate of negative 3. And sure enough, from the graph, we have a horizontal line at y equals negative 3. So that verifies that. Okay. So notice a little bit more involved to find all of these components, particularly since we're transitioning from the vertex to the focus, which is involved enough as it stands, but then from the focus to 2 additional points on the graph. So we end up having to make a couple adjustments, the kinds of adjustments that are a little bit more straightforward when we're centered at the origin, become a little bit more complicated when we're no longer centered at the origin. So, based on that, let's talk about the standard form versus non-standard form issue, and we'll also graph one additional parabola just to wrap it up. So we talked about with hyperbolas, with ellipses, what happens when you have an equation that actually represents one of those conic sections but doesn't really fit into standard form. Well, we can put it in standard form, completing the square, and we've seen what that looks like in 2 different cases. Now we can use the same strategy for a parabola, but we have to keep in mind that a parabolic equation is a little bit different. It's different in the sense that it only has one squared term, whereas the equation for an ellipse, the equation for a hyperbola, both x and y are quadratic. So because we only have one squared term, we only have to complete the square once. We only complete the square for the term that is quadratic. But it also means that some of the other work we do is just going to be a little bit different. So once we complete the square, once the equation is factored, we have to divide out whatever the coefficient was that we isolated, that we factored out, and then we're going to factor the linear side of the equation as well. So essentially completing the square is going to look the same, but because we're only completing the square with one of our variables, the way we adjust the other side of the equation is going to be a little bit different. So we only need to isolate and group the variables related to what we're going to complete the square for. So anything that's not related to that variable that's squared is going to go to the other side of the equation. So this is where the strategy varies just a little bit from what we did with an ellipse, what we did with a hyperbola. Okay. So let's just start by writing in standard form. Again, the goals are the same. Find all the key features, graph the parabola, write the equation for the directrix, the axis of symmetry. Finding all of those features means we need to find our standard form first, though. Okay, so notice we have a quadratic x and then a linear y. So that's our indication that we're looking at a parabola versus an ellipse versus a hyperbola. So we're going to complete the square with x. Now we don't complete the square with y. So normally we just move the constant over because we're going to have to complete the square for both variables. That's not the case here. Y, we don't have to complete the square. So we're actually going to move both the constant and the y term, the linear term that we're not completing the square for. So the only thing that's going to stay on the left-hand side of the equation are the terms related to that quadratic x. So we're left with 4x squared minus 20x is equal to, now add the 8y, so plus 8y, move that over, and then subtract 57. So as with our normal completing the square procedure, we kind of just bring the right-hand side along for the ride. We're really going to focus on what's on the left-hand side, completing the square. So we're going to factor out the coefficient on our x squared. So that's going to be 4 times x squared minus 5x, and that's equal to 8y minus 57. And then we need to complete the square. Now it's going to be a little bit more involved here simply because the value we add on is not going to be as pretty as it normally is. So we're dividing by 2. We're taking negative 5, dividing it by 2. Well, immediately 2 doesn't go in evenly to negative 5. So that's my indication that these numbers are going to be a little bit different. So divide by 2 and then square it. Well, if you're worried about doing that by hand, do it in your calculator. So we're taking negative 5, we're dividing it by 2. So don't worry that it's a decimal right now. We'll convert it back to a fraction in just a moment. So we're dividing by 2, and then we're taking that result and we're squaring it. So notice we get a positive number. That's expected. Anytime we square, the result of squaring is going to be positive. Now we want the fractional version of that, so we're going to go convert that value to a fraction. And so we get 25 over 4. So that's the value we add on to complete the square. So we have 4 times x squared minus 5x plus 25 over 4 is equal to 8y minus 57, and then balance the equation. So we added on 25 over 4 times 4, so do it the same thing on the other side. Now, if you're concerned about factoring this, don't be. It can be factored, and there's kind of a shortcut here. So you may have noticed a pattern for how these perfect square trinomials factor. So let's write down what we actually added on here. So we took negative 5, we divided it by 2, and then we squared it. This value inside parentheses is what's going to go into our binomial when we factor. And that's always going to be the case. Anytime we factor a perfect square trinomial, the value that was squared in order to complete the square is what we end up adding on in order to generate our binomials. So when I factor this, that's going to end up as x minus 5 halves squared. And I can verify that, of course, by FOILing this out. If I were to FOIL this out, I'll find that I get back to this. You might take a moment and pause the video and just verify that that is in fact the case. Because factoring when we have something like this, it's fractional, is maybe a little bit just more involved than we normally see. So what about the other side? Well, we've got our 8y, and then we can combine our constants. So negative 57 plus 4 times 25 over 4. Well, that's not as bad as it originally looks, because notice these 4's, they divide out and reduce to 1. So we're really only looking at negative 57 plus 25. So negative 57 plus 25, and that's going to give us negative 32. So minus 32. So here's where we need to follow those additional directions. So our equation is factored. So now we're going to divide out that isolated coefficient. Keep in mind our standard form, if we look back at our standard form, we like to have the quadratic factor isolated, which means that coefficient that we have right now, we want to get rid of that. We want to divide that out. So I'm going to divide out the 4. Now what does that mean on the left-hand side? It just means that that factor of 4 reduces. It doesn't mean we're dividing in here, it just means we're canceling out that particular factor. However, on the right-hand side, because the right-hand side is not factored, each term needs to be divided by that factor. So we have x minus 5/2 squared. 8 divided by 4 is going to be 2, so we have 2y. And then 32 divided by 4 is going to be 8, so minus 8. Now we're almost there, not quite. Let's look back at that standard form one more time. So what do we have? We have a quadratic x, so we're in this case. But notice we also like to have the right hand factored. So the coefficient on y, we also factor out that value. So I'm going to factor out this 2 on the linear side. So I have x minus 5/2 squared is equal to 2 times y minus 4. That is going to be our standard form. Let me box it in so we know what we're looking at. That's going to be our standard form. That's the form we use to find all of the graph's components and to generate the graph. So you'll notice we have a fractional value. Something else kind of different has happened here as well, something we haven't encountered before. Look at the value that's going to give us p. So we know that 4p is going to be equal to that value, which means that p is going to be 2 divided by 4, which is 1/2. So not only do we encounter a fractional value associated with our vertex, but our value for p is also going to be fractional. And unfortunately, these kind of numbers are realistic. We need to be comfortable encountering and dealing with fractions, which is why we're doing an example like this. So let's look at our vertex. What's that going to be? Well, we have negative 5/2, so the x-coordinate of the vertex is positive 5/2. And then we have y minus 4, so the y-coordinate is going to be 4. Now, for purposes of graphing, you might want to do 5/2 in the calculator, divide it, make sure you know what that is. So that's really 2.5, 4. So that's going to be our vertex. And let's go ahead and put that on the graph. So 2.5, 4. So just ballpark it, do your best. Your x-coordinate is halfway between 2 and 3, and the y-coordinate is 1, 2, 3, 4. So there's our vertex. Okay. So what about our focus? Let's think about what we're looking at. What kind of equation do we have? What's the structure tell us? Well, x is quadratic. So because we have x squared, that means we're looking at something that is horizontal. So either, not horizontal, vertical. Apologies. That is vertical. Okay, so either opening upward or opening downward. Now we look at the coefficient. So 2. 2 is a positive coefficient, which means we're opening in the positive direction. So opening vertically in the positive direction means we're opening upward. So that tells us how our graph is going to be oriented. It was oriented so that we are pointing upward. Well, let's think about what that tells us about our graph then. Well, here's our vertex. So we're opening upward from there. Now, number one, that tells me if I tried to graph using x and y intercepts, I can get a y-intercept, but this graph wouldn't actually have any x-intercepts. So it means graphing from this point of view is maybe going to be more beneficial than graphing using what you normally did with x and y-intercepts. Now, our focus is going to be above our vertex by p units. So what does that mean algebraically? It means we're holding the x-coordinate positive and we're adjusting the y-coordinate. So hold the x-coordinate for the vertex positive, add on p to the y coordinate. And p is fractional, and we also have a fractional coordinate for our vertex. So we're holding our x coordinate constant, and then we're adding on p to our y coordinate. So 4 plus 1/2. Now again, let the calculator do the hard part for you. So 4 plus 1/2. There we go. Convert it to a fraction. And that's going to be 9/2. So the exact value, the fractional value, is 5/2 and 9/2. So let's graph that. Now we just showed in the calculator the new y coordinate is going to be 4.5. So the x coordinate is 2.5, the y coordinate is 4.5. So x coordinate is 2.5, the y coordinate is 4.5. So we already were 4 units up. The focus is just half a unit above that. And I'm going to graph it small, otherwise it's going to look like these points coincide with one another, which they don't. So half a unit above, since p is 1/2. Now from there, if we were to transition across our focus from one side of the parabola to the other, we draw the latus rectum. We have the focal diameter, the length of that line segment. So what is the focal diameter? So it's always going to be 4 times the absolute value of p. Well, in this case, p is 1/2. Its absolute value is 1/2. So that's going to be 4 times 1/2, which is 2. Which means it's going to be half of that distance, 1 unit, to the endpoints of the latus rectum. I'm running out of space, so I'll just say 1 unit to latus rectum. Now let's graph that, and then we'll look at that algebraically. It may be easier to graph it first and then think about what the algebra tells us. So we're starting from the focus, and we're going 1 unit in either direction, in this case to the right and to the left, to get to the endpoints of our latus rectum. So 2 units total across. Now keep in mind, we are halfway between 2 and 3, which means if we travel a full unit, we're halfway between the next pair of integers, which means we have a point here, roughly, and here, roughly. So along the same horizontal segment as the focus, but 1 unit to the right and to the left. And as before, technically that's enough to graph. So we can go ahead and finish out the graph based on that, and then we'll just focus on the rest of the algebra. Okay, so what are the coordinates of those endpoints? So remember, we're starting at the focus, and then since we have a vertical parabola, we're going to the right and to the left of the focus this many units. So in other words, we're holding the y coordinate constant at the focus, and we're increasing and decreasing the x coordinate. So x coordinate 5/2 increases and decreases by 1 unit, and then we're holding our y coordinate constant at 9/2. And again, let the calculator do the hard work here. Don't get overwhelmed by the fractions. Your calculator will handle that for you. So 5/2 plus 1. Now convert it back to a fraction. That's going to be 7/2 and 9/2. Let's verify that that makes sense with the graph. So we said that one of the endpoints was going to be at 3.5 and then 9/2, which was 4.5. So do we have a point at 3.5 and 4.5? Well, 3.5 and then 1, 2, 3, 4, 4.5. There we go. So that's going to be that particular point right there. Now, next one. If we were to take 5/2 and subtract 1, so 5/2 minus 1, and then if we convert that to a fraction, that's going to be 3/2. So the other ordered pair is going to be 3/2 and 9/2. So in other words, 1.5, 4.5. So let's check that one. So 1.5, 1, 2, 3, 4, 4.5. So that one checks out as well. Well, there's the hard part. Finding those, definitely the hard part. So let's finish with our directrix and then our axis of symmetry. So where would the directrix be on this graph? Well, if the focus is above our vertex, that means the directrix is going to be equidistant below. So we're talking about a vertical parabola, which means we have a horizontal directrix. So it's going to be of the form y equals, we're starting at the vertex, which has a y coordinate of 4, and then we are subtracting p. So it's p units, in this case, below. So if the focus is p units above 4, the directrix is p units below 4. So 4 minus 1/2. You may not even need to do this one using in the calculator, but just for the sake of doing it, if it helps, that's going to be y is equal to 7/2. So 3.5, let's verify that that would in fact be the location of our directrix just based on the graph. So half a unit above takes us to 4.5, half a unit below takes us to 3.5. So that does make sense that that would be the equation we get. And then last but not least, the axis of symmetry. The good news is once we get to this point, we don't have to do any extra algebra. So for a vertical parabola, the axis of symmetry is a vertical line. It's the vertical line that passes through our vertex. So the x coordinate is going to give us this value for our line. So x is equal to 5/2. So I wanted to show you an example like this, not to overwhelm you, but to show you that even when the numbers feel overwhelming, it's still doable. Fall back on the shape, understanding the shape of the graph, how all those different key components are related to one another, makes the problem manageable. Don't become overwhelmed by fractions. Unfortunately, fractions are reality. Eventually, you're going to encounter some fractions. Numbers aren't always going to be pretty integer numbers, but it is doable with fractions as long as we pay attention to structure and what we know about how all of those components of our graphs are going to be related to one another. So that concludes our discussion of conic sections. So just to recap, simplest conic section, we have the circle, and I'll make a couple notes here on our last page just to summarize. So simplest conic section is a circle, general form for a circle, something of the form x minus h squared plus y minus k squared is equal to r squared. So notice we don't see any denominators here. It looks similar to the form for an ellipse. Biggest difference is we don't have a denominator here. We have a value over here other than 1. Essentially, you can think of it as if we were to divide out this number like we would to get a standard form, both of these denominators are the same. So the fact that those denominators would be the same is what makes this a circle rather than an ellipse. So for an ellipse, we have something of this form, either x minus h squared over a squared plus y minus k squared over b squared is equal to 1. A is always going to be the larger denominator. Both are positive, so the order we write them in doesn't matter. A and B does not depend on order. A is always defined as the larger of the two values, so we could also have something of the form x minus h squared over b squared plus y minus k squared over a squared. So notice I didn't change the order of the terms, but I changed the labeling for the denominators. We always think of a as being the larger of the two values. So if a is associated with the x term, that means we have a horizontal ellipse. It's elongated horizontally. If a is associated with y, we have an ellipse that's elongated vertically. Now we also have the hyperbola. which looks very similar in form to the elliptical equations with one major difference. We change to subtraction. Also, the way we determine A and B changes. So A is always going to be the value associated with our positive term, since once we change to subtraction, we now have a positive and a negative term. So this is going to be one form, so x minus h squared minus y minus k squared, and then a squared and b squared. Again, a is always associated with our positive term. And then we also could have y minus k squared over a squared minus x minus h squared over b squared is equal to 1. And then last but not least, the parabolas, what we looked at in this section. And as we've seen, the conic section form for our parabola, the standard form, is a little bit different than what we're used to seeing. It just gives us a slightly different perspective and gives us different information about how we would graph a parabola. So we can have something of the form x minus h squared is equal to 4p times y minus k, or we can have something of the form y minus k squared is equal to 4p times x minus h. So it looks like a lot, but keep in mind we find pretty much everything we need just from the constants we see in the equations. So with an ellipse, h and k, of course, that's going to be important. That tells us where the ellipse is centered. Same thing for a hyperbola. The a and b for an ellipse tell us what we need to know about our major and minor axes. So anytime a is associated with x, that means we have a longer horizontal axis. When a is associated with y, we have a longer vertical axis. And then b tells us what the minor axis is going to look like. So the major axis is length 2a, minor axis is length 2b, passing through that center at h comma k. And that pretty much gives us enough to graph. For a hyperbola, again centered at h comma k, based on what's associated with x and y, a is going to tell us how to get to the vertices, either the horizontally distributed vertices if a is associated with x, or the vertically distributed vertices if a is associated with y. And then we know we have asymptotes for a hyperbola. We graph using those asymptotes. We use the box method, so you definitely want to review that. And then we talked about parabolas in this section. We have 4 different kinds of parabolas: opening upward versus downward, opening right versus left, and we know what to do there in this case now. So based on these forms, we have pretty much everything we need to know just from these constants. So focus on finding those constants, focus on the structure of what the graph is going to look like based on the structure of the equation. Try not to memorize formulas too much. That's kind of dangerous when we talk about conic sections, just because there's so much involved. There's so many formulas, there's so many slight differences in how we find different components from one particular conic section to the next. So understanding the structure of the equations, understanding the structures of the graphs, how the different components relate to one another is going to make graphing these a little bit more manageable.